Given the relation R containing two ordered pairs 1, 2 and 2, 3 on the set A, which contains the elements 1, 2 and 3. Add the minimum number of ordered pairs which when added to the relation R make it an equivalence relation. Okay, let us begin. Now we know that any relation R is said to be an equivalence relation if it is reflexive, it is symmetric, as well as it is transitive. Let's quickly go through the definition of each of them. Now, a relation R is said to be reflexive if we have the ordered pair A, A belonging to the relation R for all A belongings to the set A. That means in our case, we have the set A containing three elements 1, 2, 3. So if we are to pick up the element 1, then the ordered pair 1, 1 must belong to the relation R. The element 2, 2, if we pick up the element 2, then the ordered pair 2, 2 must belong to the relation R. And for the element 3, the ordered pair 3, 3 must belong to the relation R as well. Only then we can say that R is reflexive. So that means our relation R must contain these three ordered pairs 1, 1, 2, 2 and 3, 3 for it to be reflexive. Next, let's check for symmetry. For symmetry, if we have the ordered pair A, B belonging to R, then B, A must also belong to the relation R for all A and B belonging to the set A. Now in our case, in the relation we have 1, 2. So here we have 1, 2 belonging to the relation R. Now for R to be symmetric, it demands that the ordered pair 2, 1 must also belong to the relation R. Fine. So that means we need an ordered pair R 2, 1. So let's make a tally of all of this as we move along. So R contains the ordered pair 1, 2 and 2, 3. This is already provided to us. Now for it to be reflexive, we have shown that 1, 1, this ordered pair, the next ordered pair 2, 2, and then we have 3, 3 that must belong to it as well. And then for symmetric, if 1, 2 belongs to R, then 2, 1 must also belong to the relation R. Then we have 2, 3 belonging to R, which means that 3, 2 must also belong to the relation R as well. Then we have 3, 2 belongs to the relation R. And then we have transitivity. So here the relation R is going to be transitive if for two ordered pairs A, B and B, C belonging to R, A, C must belong to the same relation R as well for all values of A, B and C picked up from the set A. That means if we have the ordered pair A, B and B, C, and it's very important how we choose these ordered pair. As we can see here, the second element in the first ordered pair A, B must match with the first element of the second ordered pair. So that means for our case, if we have 1, 2 belonging to R and we have 2, 3 belonging to the relation R, then transitivity demands that 1, 3 must also belong to the relation R. Only then we can say that the given relation is transitive. So that means we need an ordered pair 1, 3. However, we have to be careful here. We cannot stop here. If we are considering 1, 3, we'll need to consider 3, 1 because the relation R is symmetric. If 1, 3 is present, 3, 1 will automatically be present. Now these are all the ordered pairs that must belong to the relation R, and once we add all of these extra ordered pairs, then the relation R becomes equivalence relation because that relation is reflexive, symmetric and transitive. So what is the minimum number of ordered pairs that we need to eat? So we need to add 1, 2, 3, 4, 5, 6, 7. So 7 ordered pairs, 7 ordered pairs, and namely 1, 1, 2, 2, 3, 3 and the remaining needs to be added. These needs to be added to the relation R to make it an equivalence relation.